Alright, so this is June 2013 Applied Physics paper. So let's get straight into it. So we've got the turntable of a microwave oven has inertia 8.2 times 10 to the minus 3 kilograms meters squared, and it's about a vertical axis of rotation. With the drive disconnected, the turntable is set spinning, starting an angular speed of 6.4 radians per second, and it makes 8.3 revolutions before coming to rest. Calculate the angular deceleration of the turntable, assuming it's uniform. So the fact they told us uniform means you're using an angular Suvac equation. So what we've got final speed, we've got displacement, and we've got initial speed. So we want to essentially use this equation. Okay, so we want to, well that's 0, so we've got, what's that, 6.4 squared divided by minus 2 times 8.3 times 2 pi to convert it into radians, and that's going to be equal to the acceleration. So let's get the old calculator out. 6.4 squared divided by 2 times 8.3 times 2 times by pi is equal to 0.3927 dots. So we're getting it to two significant figures because all the data in the question is, and the unit of angular acceleration is radians, s to the minus 2. Okay, so calculate the magnitude of the frictional torque. So torque is equal to the moment of inertia times the acceleration. So it's the 0.3927 ... times by, let's scroll back up for the inertia, 8.2 times 10 to the minus 3. So let's take our unrounded answer, times 8.2 times 10 to the minus 3 gives us 3.222, so it's just going to be 3.2, two significant figures, Newton meters. It's now reconnected and a circular pi is placed centrally on the turntable. Power input of the oven is 900 watts, and to cook the pie, the oven is switched on for 270 seconds. Turntable reaches operating speed of 0.78 radians per second almost immediately, and the frictional torque is the same. Calculate the work done to keep the turntable rotating for 270 seconds at a constant angular speed of 0.78 radians. So work done is torque times by theta. So torque we know is 3.22 10 to the minus 3. Oh wait, I think I forgot to write that. Yeah. There should be a times 10 to the minus 3 in there. My mistake. 3.22 times 10 to the minus 3. And your angular displacement is going to be 0.78 times by 270, so that's the angular displacement in that time, and so let's multiply. 0.78 times 270 gives you 0.8, so it's going to be 0.68 using your unrounded versions. Okay, moving on. Show that the ratio of energy supplied to the oven divided by work done to drive the timetable is of the order of 10 to the 5. So the energy supplied is the power. So what we're doing energy is power times time. So energy in the power times by 270. Okay, and that gives us a value of 900 times 270 is 243,000, which is approximately 2.4 times 10 to the 5. Work is, what was it, 0.67. So ratio divided by 0.67, 3.6 times 10 to the 5, which is approximately an order of magnitude of 10 to the 5 there when you divide them, when you essentially divide the value we've got for the energy in divided by the work we get out. Alright, let's move on. Okay, so we've got a diver, and we're looking at how they're falling and looking at how the moment of inertia of the diver changes as they adjust their position. So explain how moving the legs towards the chest causes the moment of inertia of the diver without the axis of rotation to decrease. So remember, the moment of inertia is essentially a sum of the masses that make up the system and the distance from the center of rotation. So the key thing here is the mass is the same, but when they adjust their position, it's concentrated closer to the axis of rotation. Therefore, R decreases, and then putting those two statements together, the moment of inertia decreases. Okay, so that's the key thing. So we've got, this is what moment of inertia is. It's the sum of the particles and their multiplied by their distance squared to the center of rotation. Mass is the same, but it's concentrated closer to the axis of rotation. Therefore, the R decreases, so I decreases. Those are the stages there. Explain in terms of the angular momentum why angular velocity varies during the dive. So, key thing is no external torque acts. Therefore, angular momentum is conserved. So the moment of inertia times the angular speed before equals the moment of inertia times the angular speed after. Okay, so the moment of inertia is decreased, therefore angular speed is going to increase in order to keep essentially make them equal to each other. So in terms of how the angular velocity varies throughout the dive, I'm just going to take a look on my computer screen to see what the graph looks like. So we're starting off with a very high moment of inertia. So you're going to start with a very small angular speed, which is going to increase, and then it's going to decrease, but the angular velocity is going to be greater at the point it hits the water than it was to start with. So let's see. The first thing that happens is the angular speed increases. And it's at the beginning you actually have the maximum rotational acceleration because you have the biggest change in the inertia at the beginning, and then the angular speed later decreases and then but the final angular speed is greater than the initial angular speed there, because you can see the inertia at the end is slightly less than it was to start with when it enters the water. Okay, so let's move on to the next one. At time t, the angular velocity of the diver is 4.4 radians per second and the moment of inertia is 10.9. With reference to figure 1, calculate the maximum angular velocity of the diver during the dive. So what we want to do is find the minimum moment of inertia. So reading off the graph, that is 6.4 kilogram meters squared. So let's first calculate what the total angular momentum is. So 10.9 times by 4.4 . Okay, so the angular max is going to be total angular momentum divided by I min. So that's going to be 47.96 divided by 6.4. Let's divide that by 6.4, and we end up with 7.49, which is going to be 7.5 to the correct number of sig figs. Okay, so moving on to look at an engine, and we're looking at a diesel engine. So let's take a look at the first one. Explain why the compression stroke of a diesel engine is considered to be an adiabatic change. So first of all, what is an adiabatic change? So adiabatic means no heat exchange with the surroundings. So that will be the first part for the first of the 2 marks. And so in order to have a process that's adiabatic, it must happen incredibly quickly. So there's no time for heat exchange. So yeah, the process happens very quickly, giving no time for heat exchange. Alright, so we've got figure 2 shows the cylinder of a diesel engine. The pressure of the air at the start of the compression stroke is 1 bar, and the volume is 4.5 times 10 to the minus 4. We've got the same cylinder later on, but we've got a new pressure. Compression is adiabatic with no leakage. So if it's adiabatic, we know that P1 V1 to the 1.4 is equal to P2 V2 to the 1.4. And we want to find the final volume. So we want V2 is going to be P1 V1 to the 1.4, and we want the 1.4th root of that. So that's going to be the 1.4th root of 1.0 times 10 to the 5, and that's going to be multiplied by 4.5 times 10 minus 4, but that's all to the power of gamma, so 1.4, and divided by 6.2 times 10 to the 6. So let's work through 4.5 times 10 to the power of minus 4. We want to do that to the power of 1.4, so let's find the power of 1.4 times by 10 to the power of 5, divided by 6.2 times 10 to the power of 6. And we want to do the 1.4th root of that. That's on the inverse one of the x to the power of whatever you like function. And you end up with 2.36 times 10 to the minus 5. So rounding it, that's going to be 2.4 to 2 significant figures. Okay, continuing on. The temperature of the air in the cylinder at the start of the compression stroke is 297. Calculate the temperature just before the fuel is injected, so we're going to be using our old friend, the ideal gas equation. V1 over T1 is equal to P2 V2 over T2, and we want to get T2, so it's going to be P2 V2 T1 over P1 V1, 6.2 times 10 to the 6 times by 2.36 yada yada times 10 to the minus 5 times by 297, our temperature is already in Kelvin, and then divided by 10 to the 5 times by 4.5 times 10 to the minus 4. So let's put that in the calculator. So I've already got the answer to the previous question, so multiply that by 297 times by 6.2 times 10 to the 6 divided by 10 to the 5, 10 to the 5 to 4.5 times 10 to the minus 4, and that comes out as 965.758 blah blah blah, which would round to 9.7 times 10 to the 2 Kelvin, or it's 965. The mark scheme for the question might say something different because I've used unrounded values in here, as you should, but I believe the mark scheme allowed you some rounded ones as well. Explain why in a diesel engine the fuel starts to be injected into the cylinder slightly before the piston reaches its highest point. So essentially what you want to do is vaporize the fuel. So the fuel needs to be vaporized, very vaporized. Therefore, the heat of the gas in the piston is going to vaporize the fuel before it gets to ignition, or before it gets to the top dead center of the engine, the highest position of the engine when the volume is the smallest. Figure 4 shows the indicator diagram for a real diesel compared to the ideal. Compare the real engine cycle with a theoretical cycle. You should discuss the important differences between the two cycles, so we're going to highlight those in a second. And the overall efficiency is less than predicted. Okay. So let's highlight a few of the key differences. So it's like a game of spot the differences. We've got this exhaust and induction loop in a real engine, and we've got these rounded corners appearing here on the cycle, and we've got what are almost certainly not adiabatic processes go, which is why I've put a big cross next to them. So those are the key things. So let's put that into words on the text on the next. So real cycle has an induction exhaust loop, and what this is doing is pumping out the gas and getting in fresh oxygen, and so which it uses work, and that lowers the efficiency. If it's taking work, it's taking what could be useful, and it's essentially wasting it, pumping that in and out. So it's going to lower the efficiency of your engine. You've got a smaller enclosed area, and that giving a lower indicated power. So if your area is smaller, that's a lower indicated power, which giving, if you have a lower indicator, it's going to give a lower efficiency, because we're still putting the same amount of fuel in, but we're just getting less back at the end, so it's going to give us a lower efficiency. Okay, so the other thing is we had the rounded corners on there. So one of them was at constant pressure and one of them was constant volume. So in a real cycle, constant volume is impossible. And that's because the engine or the piston never stops. So that's another difference there. We also need to think about the fact that incomplete combustion occurs. And that's going to give it a lower output power, output power, and thus efficiency. Is there anything else we can say about that? Oh yeah, the compression, expansion are not infinitely quick. So therefore they are not adiabatic, and therefore we shouldn't use such abbreviations, but therefore you're going to lose lost to surroundings, and again that's going to give you lower efficiency in your engine. And finally, in a real engine, you're going to end up doing work for other things. So you're going to do against frictional torque, at bearings, and you're going to do it pumping engine fluids, so like cooling water, oil, all those kind of things. And doing that is wasted energy, so again gives you low efficiency. So there are so many things you can write about for this question that you can pick up. There's a difference between a diesel and a real diesel and an ideal. It's a very nice longer answer question to give you because there's so much you can talk about comparing them. Explain what is meant by a reverse heat engine. So with the reversed heat engine, you're putting work in, because with a heat engine you're taking work out. So it's going to be a device when you input work, because you're putting work in, heat is transferred from your cold space to the hot space. It is going the reverse of the way it really wants to, and that's why you have to input work, because you're making it go the opposite of the way to which it would decide to by itself. Explain why the coefficient of performance of a reversed heat engine when operating the heat pump is always greater than the same reversed heat engine as a refrigerator. So let's draw an example setup. So you put work in, Q out, and then you end up with Q in. And this is your hot source, and this is your cold source. So the coefficient of performance of a heat pump is going to be Q in over W. Coefficient of performance of a refrigerator is Q out, because that's the useful energy, over W. And then you know Q out plus W equals Q in, so therefore you know that COP heat pump is going to be greater than COP refrigerator because the top line is going to be bigger. So that's what it's going for there. And that completes this paper.